Take a completely straight pen and drop it into a glass of water. Look closely at the liquid line. The pen appears to snap into a sharp angle exactly where it crosses the surface. But if you pull that same pen back out, the plastic is undamaged. The physical object hasn't changed shape at all. To understand why this happens, we have to remember that human eyes don't actually see physical objects. We see the light rays that bounce off those objects, changed shape at all. To understand why this happens, we have to remember that human eyes don't actually see physical objects. We see the light rays that bounce off those objects. In empty space, those rays travel in straight paths directly from the pen to our eyes. The question is, what happens to that perfectly straight light path when we pour water? Creates resistance. A light ray traveling up from the bottom section moves at a slow, restricted pace, similar to a person trying to walk through a crowded room. The moment that light ray crosses the boundary and escapes into the thinner air, the resistance drops. The light experiences a massive and immediate acceleration. Every time light crosses a boundary between two different refractive indexes, a change in velocity is guaranteed. To measure exactly how this speed change affects the light, we use a tool called the normal line. This is an invisible, perfectly vertical reference line drawn exactly perpendicular to the boundary surface. Let's track a single ray of light bouncing off the submerged pen tip. It travels diagonally upward through the water, heading straight for the point where the normal line meets the surface. Right as the ray hits that exact intersection point, the lower refractive index of the air takes over. The acceleration begins instantly, but because the ray hits the boundary at an angle, one side of the light wave speeds up before the other. This uneven acceleration physically forces the trajectory to flatten out, pivoting sharply away from the vertical normal line. That dual action process is the precise definition of refraction. The light changes speed upon entering a new optical density, and that change in speed forces it to change direction. Now, we follow that newly where the pen is, the brain reverse engineers the path. It projects a straight line backward from the exact angle the light hit the eye, completely ignoring the bend that just occurred at the water surface. Because it traces this shallow angle backward, the brain's projection line stops at a false location. It renders a phantom pen tip at a significantly higher elevation than where the true object is actually resting. The bent pen you see in the glass is a constructed image. It is an